Hello and welcome to this week's webinar, Focus on Geothermal Energy for the Weekend by Think Geoenergy and Enerchange. My name is Alexander Richter. I'm the founder and principal of Think Geoenergy in replacement for Carlo. Unfortunately, he was not able to join today. With us today is Sigurdur Markusson, the project leader for the Superhot program, the IDDP program at Reykjavik Energy. A project that brings together Icelandic experts here in the third iteration of this project, but we'll learn probably more of that from Siggy. Of course, superhot geothermal is a really hot topic in the truest meaning of the word, and with international projects pushing here the boundaries, it's definitely interesting to hear from a project that has already drilled twice. And is now planning to drill for the third time. So, Siggy, with that, over to you. But of course, you have, for the audience, you have the possibility to ask questions. You can do so in the question panel of the webinar. Put your questions in there, and we'll try to answer them as much as possible after the presentation. And with that, I hand over to Siggy. Siggy, thanks for joining us.
Thank you, Alex, and it's a pleasure to be here and share our project with all of you. I'm going to talk about IDDP-3 and this journey that we have been on in this IDDP project since the year 2000. And this is not only now a single well project. We have decided to expand our research plan a bit to try to get a broader reach over kind of the topics and issues we are trying to solve. But if I go back a little bit and tell you about what Reykjavik Energy is. So Reykjavik Energy is owned by the city of Reykjavik. So Reykjavik Energy is the parent company of multiple subsidiaries, one being On Power that operates our geothermal power plants at Hellisheiði and Nesjavellir. And then we also operate utilities, fiber optics, and carbon sequestration. And this is a picture of our plant in Nesjavellir. That is 120 megawatts, but was built originally for district heating for the capital area of Reykjavik. So here you can see a aerial photo of the site and the capital area to the left, and these two sites, they are both part of this volcanic system here called Hengill. And those here with a geoscience background or interest can see maybe the kind of the structures here that these locations are exactly on the plate boundaries that run through Iceland. So this is a very active area in geological terms, and I will get back to that later. But Reykjavik Energy has been in this business for a century. We started we were created by the city of Reykjavik in the effort to heat up the city. So we operate now one of the biggest district heating systems globally, or at least they used to be. And then later in the 20th century, we started electricity production in the Nesjavellir field, and then we built up the Hellisheiði plant. And we look at this as like the two, big steps, the two generations of geothermal that we've gone through here in Iceland. And now we are looking at superhot geothermal as kind of the third big step that can take geothermal forward and really impact how we utilize geothermal and how we approach geothermal and create value for society out of the resources. And this interest in superhot geothermal began by drilling of well NJ11 in Nesjavellur. The crew of the rig intersected a very powerful, very hot reservoir at 2.1 kilometers depth. They don't know how hot actually it was, but the thermometer used, it maxed out at 380 degrees C. And since they didn't have any equipment and the well wasn't designed for this type of conditions, they just filled up the topmost 500 meters, if I remember right, with gravel, and just closed off this hottest part. And then over the next 35, 40 years, it was just a rule that you would not drill deeper than 2,000 meters in Nesjavellur to avoid hitting these superhot formations, because we didn't have any as I said, way to utilize it. But what is the challenge of going deeper? This is kind of a question I get a lot. Why don't we just use the same solutions, the same technology as we are going deeper? And of course, there are few different reasons why this is difficult, but drilling itself deep is not, this is not even deep in all comparison. This is here in Iceland, we are seeing these formations maybe at 2 kilometers, and drilling down to 2 kilometers is business as usual, and wells up to 6-8 kilometers in other industries are common. But the temperature and the steam itself causes a lot of issues, and so the equipment we have traditionally been using cannot handle these conditions. There always been this kind of idea that in geothermal systems, when you go below certain temperature, there is no permeability, and go above 350 C, there is no permeability, and so at least this was the idea for a long time. So this has been, so we have known about these resources for a long time, but the technology development needed and kind of the cost and effort still waited for a long time. It wasn't until later that we started this for real, but the idea behind this is very clear. You're striving for a better efficiency, so you get more energy dense fluid. You can get more out of each well, and hopefully with time, with constant innovation and continuous development, you can lower the per megawatt cost. So this is kind of, I would say, the same effort as you see in all industry. You're always striving for higher efficiency. And in the context of Iceland, this is also very interesting in just terms of the geology we are in. Now geothermal is especially high temperatures for electricity production is kind of confined to volcanic areas that are on this tectonic plate boundaries and defined to the kind of the fracture zone around these volcanoes. So this is where you have all the big geothermal power plants in Iceland. But if you look at the thermal gradient map, so this is a map that is based on all well data from Iceland, and we see that the thermal gradient at 1 kilometer is of course very high all along the plate boundaries that run through kind of the Reykjavik Peninsula in the west, in the lower left corner, and up in the east, but we believe that if you can drill deeper, if you can go into hotter formations, and especially if you manage to get a hold on this technology and also develop ETS technology at the same time, you're no longer bound to the central volcanoes or the fracture zones around the central volcanoes, like we have been drilling in here in the Hengil region. We are more confined by maybe the plate boundaries that have this very high thermal gradient, and that means we can expand potential production zone a lot. So this is kind of the two things we are shifting our focus towards is both super hot technology, the technology we need to finalize kind of the design of wells that can withstand these conditions, and also dive into how we can increase permeability in volcanic regions and in volcanic rocks. The Icelandic geology is mainly just basaltic rocks, highly fractured by nature. But so it's a little bit different to traditional EGS, but this is something so requiring different approach. But this is something we are highly interested in taking forward. And as you can see, this is then would apply to a big part of Iceland, and not only to the region highlighted here, but also to the kind of older active part of Iceland that still have high thermal gradient. And this is also in the context globally. This is a very relevant all over the world. You have these plate boundaries that run through the entire globe, divide the continents, and results in volcanic activity all over, and also have huge impact, hundreds of kilometers or more outside of the active plate boundaries in kind of systems that are impacted and or activity have shifted some hundreds of thousands or millions of years ago, but are still with a high gradient. But today we have been stuck with this within this barrier of 350, 370 degrees, and few attempts have been made to go over this limit, but it always seems to fail on the technology can't handle the fluid chemistry or the conditions, or there is no permeability. And it's the same story almost with all the test cases that have been done. But we are kind of stuck within this circle here in terms of electricity production with geothermal. Probably 80%, 70%, 80% of the global production is within this circle here. But if we look at the global context, the plate boundaries running around the world, and where you find a very high thermal gradient, this could kind of take geothermal to be scaled up and be more of a more important kind of solution in the renewable energy options that we have. But the key issue for this is to solve this, the technology and understand how we can create permeability where there is no permeability at a cost that works for the local energy markets. So the attempts in Iceland started with the Icelandic Deep Drilling Project. The project was created in the year 2000 by the three big energy companies in Iceland, Reykjavik Energy, Landsvirkjun, and HS Orka, and also the government of Iceland, and then later some international corporations joined the IDDP project, such as Statoil or now Equinor, and Alcoa. And the IDDP project has from the beginning been working with scientists, research institutions, and companies from all over the world. So this has really been a collaboration platform for almost 3 decades. And if I think about the impact of this collaboration, there are probably published papers that are getting close to 100 just on research related to this project. So the original contract between the companies was to drill 3 wells. Each company would drill 1 well. The first one would be in Krafla, north of Iceland, the second one in Reykjavik, and the third one in Hengill, by Reykjavik. So the first one was drilled in 2009 and the second one in 2016. And now it's time to drill a third one. Originally, this timeline was supposed to be much shorter, but because of the challenges we have learned and the time it takes to address them and test them and so on, the timeline has stretched a lot. So the first well that was drilled in Krafla in 2008 and 9 was supposed to be between 4.5 and 5 kilometers deep. And the idea was to drill between 2 known magma chambers in Krafla, something that had been defined by a lot of research in the past. There had been volcanic activity there between 1975 and 1984. So it was probably one of the most heavily studied geothermal sites globally. But during drilling, the rig or the bit got stuck at 2,100 meters. At first, they didn't understand what was happening, but after 2 attempts of sidetracking, fragmented glass got to the surface. Before that, they lost all the circulation water, so nothing was returning to surface. So then the crew understood that they were drilling into magma, but even though the depth goal was not reached, the team decided to install a liner in the lowest 100-meter part and to try to flow test the well. Even though it was hit magma, there was a high curiosity on the properties of the area just above the magma, and so it was decided to flow test the well, build a surface equipment for the flow test, and this was how it looked like in the flow test in 2011. What you see is probably 50 kilos per second of steam, highly superheated, 3,200 kilojoules. But these fluids are very corrosive, and by leaving the well closed for a long time, heating up slowly, it results in corrosion of the casing and the liner, and this is the reason for this black color, gray color of the steam. But this color went away in 2 hours maybe, and the steam became clear and transparent, and then you can obviously see kind of the transparent part of the steam and the high degree of superheat. And so this blowing off of kind of corrosion debris is very dirty and highly visual and frightening to say, but this is how it looked like then after 2 to 3 hours, and this is how the well was flow tested for 8 months, enabling the crew to do a lot of experiments, material testing, understanding all you needed to study about the fluid properties, the possibilities to scrub the fluid and so on. And a lot of new knowledge were gained out of this, especially on kind of the behavior of this type of steam and the difference between traditional geothermal utilization, because this superheated steam has a different chemistry, and one of the interesting thing we learned and there was very limited knowledge about in the geothermal community was the presence of silica gas in the superheated steam. So not in the liquid phase, but in gaseous phase. There is of course no liquid at these temperatures and enthalpy. But during this high pressure, high temperature boiling, some of the silica precipitates into the steam phase as a gas, and this then drops out when you lower the pressure, and this resulted in damaging of equipment and so on the surface. And we studied this in detail and learned that this is highly dependent on pressure, and taught us that we have to operate these wells at least 80 bars. And this is what we concluded from our experiments, that if you operate a wellhead at lower pressure, you're precipitating silica down in the wellbore or even out in the formation. And this is nothing unique for this well. This is just behavior of silica in natural systems. But since we didn't have any samples of these type of fluids before, we just didn't know. This is well documented in other industries where you have this type of steam and you're boiling water at very high temperatures, and one of the requirements is there is no silica in the water you're going to boil. And same with hydrogen chloride, that causes the corrosion. So the challenge is, for us at least, that are used to rather benign fluids, is that chemistry is a crucial issue with if using traditional design, traditional materials, and so on. So this has become one of the main learnings from the IDDP-1. IDDP-2 then was drilled, as I said, in 2016 and 2017. It was a deepening of existing well. There was loss of circulation below 3,000 meters. So it showed that even though you are very deep into the system at high temperature, there was permeability, but issues with well integrity and cementing caused issues for the well to finalize it and flow test it. But the crew managed to retrieve cores from intervals of the lower part of the well, and the main, I would say, findings of IDDP-2 was to confirm deep permeability for one, but also confirm for the first time the presence of supercritical fluids in geothermal system. The highest temperature measurement was, direct measurement was somewhere above 420, 426, if I remember right. But that was not in the deepest part. Indirect measurements and theoretical approaches have given the temperature somewhere around 535 degrees C. So this is kind of gives us the knowledge that supercritical phase is present. And one of the big maybe learnings from both of the wells is that these formations can be productive, and there is permeability there, and that is not what will stop this technology going forward. But there's a very big need for technological development, materials to withstand the fluid chemistry, and all sorts of equipment needs to be adjusted to that, to the pressure and temperature, and to the chemistry. But this really pushed forward our knowledge on the deep resource and the fluid behavior. And this has been ever since these 2 wells were drilled, been the topic of multiple researchers and research groups working on all sorts of topics around both the engineering and earth science side of this. So I often say to my engineering friends that the resource is there, so that's what we learn. The rest is just engineering, meaning that we can solve it. I think the big question is more, can we solve it within the cost boundaries geothermal needs? And so now we are planning IDDP-3 and also what we call our Superhot development plan, or shift, as we created recently. I will tell you more about it in later slides. But so after this journey, we kind of are less focusing on the resource itself, more on finalizing the technology, finalizing the equipment to get a stable well that we can float test for a long time. So that is really the goal of IDDP-3. And also we will focus on understanding the scale of potential, the feasibility, the cost, how we can make this technology fit within the energy prices in the Icelandic energy market. And since drilling of IDDP-2, we have been involved in various big research projects, many of them financed through European grants and also some grants in US cooperation, where we have been studying some of the issues we faced in IDDP-1 and IDDP-2, and now we believe it's about time to test the technology. And one of the things we did is we applied for a new European grant to take all these learnings from previous project and do this field test that we call SHIFT. So IDDP is part of SHIFT, a SHIFT is a consortium of 17 different partners all over Europe, ranging from universities, engineering companies, Enel, for example, another power company, and companies with expertise in some of the issues we are working on solving. And so these are the steps that we have put together in this research plan, and IDDP-3 is the first step, where we are going to focus on direct superhot fluid production in similar conditions and in a similar approach as was done in IDDP-1. There we are going to look into test some of the technology, as I said, and upgrade some of the design. And then the second steps we are going to take are focused on different approach of utilizing these deeper reservoirs. Can we utilize it by injecting fluids into them and connect to the systems above? And third step is then, can we, in these superhot formations, can we have well pairs where we impact the permeability. And this is one of the things we believe we saw in IDDP-1. There have been a strong indicators that the fluid produced in IDDP-1 was fed by a nearby reinjection well. So we might already have an example of this type of system in Iceland. This is a bit different from, I would say, the EGS project now being worked on in the US. This is more, as I said, in basaltic rocks, in more already fragmented environment. But also we are thinking about kind of doing this in conjunction with the system above, and as a first step, trying to play around with natural permeability and enhanced permeability together, rather than completely isolated systems like maybe would more apply in granitic environment. And then our last step that we focus on doing in late 28 is to connect IDDP-3 with the current power plant in Nesjavellir and produce power by wet scrubbing the steam from IDDP-3 and produce some megawatts from IDDP-3. And the site we selected for IDDP-3 is the same site as we saw this Superhot resource in NJ11. And the reason for that is it's shallow, it's very well defined where it is, and this would allow us to do this, most of this as a traditional drilling project, and very little risk on the geological side, because we have drilled into it before, and two times actually, and this allows us to do more iterations, drill, test, and fail fast and continue without going for 4 or 5 kilometers to do our tests. And we have more of these shallow Superhot reservoirs in the area. We have drilled at least 4 wells where we have seen these formations spread over those. So these probably might be kind of the first focus. If we get the hang of using this technology, this would be where we see the scale-up potentials, beginning with this shallow Superhot and then go deeper. So the site this is the site in Nesjavellir. Well, NJ11 is the one here with that green circle, and we are working on the exact site selection now for IDDP-3. So these 2 wells have been drilled into the same formation. Well, as I said, NJ11 and then NJ32 in 2019. And they both show similar behavior just below 2,000 meters, very high permeability and very high temperatures. And they warm up really fast. And so this is the selected site. And somewhere between these 2 red circle is where that well IDDP-3 will be located. And this will always give us, better information on the Nesjavellir system. The picture to the left is a microseismic mapping of activity in the Nesjavellir system. And the idea is the source of these seismic activity is supercritical upflow from 5 to 6 kilometers depth, where you have a deep-seated heat source. And then when you get up to 2 kilometers, the permeability increases and the fluid is distributed to the system. On the other hand, we did not see magmatic intrusions in IDDP-1. So there is definitely a possibility that below the area at shallow depth, just below possibly NJ11, we have shallow magmatic bodies. We don't see them. We have not seen them with current geophysical instruments. But this is a very also interesting question in general for Icelandic and magmatic geothermal systems, is the heat source driven by a supercritical upflow, or is it like a Christmas tree of small intrusions and dikes that transfer heat up to the system? It's probably the reality is probably a mixture of both. We see multiple intrusions in the drill cuttings of the deeper part of our wells, but this is one of the big questions we have for this system is do we have a drillable resource down to 4-5 kilometers, or are we always confined to the topmost 2.5 kilometers? And so on the engineering side of IDDP-3, there's some issue here with, okay. Yeah, so the design criteria for the well is largely based around these issues we've been dealing with: the fluid chemistry, thermal stresses. Thermal stresses caused a lot of issues in IDDP-1, where the casings broke, and cementing resulted in water pockets in the cementing resulted in collapse of the casing. Also, thermal stresses, the joints of the casing also were torn apart, and also there is a very big factor to isolate all two-phase flow from the superhot fluid, so not mix together different reservoirs, because that results in corrosion downhole in the mixing zone of the superhot fluid and the two-phase fluid, because you will most definitely have hydrogen chloride in the superhot phase, and when that condenses, it forms acid and corrosion. So what we normally see in these wells is corrosion in the mixing zone, and scaling of silica, probably both from the two-phase boiling up, but also because of precipitation from the dry steam. So these wells tend to live very short, and just they either get blocked up or the casing collapsed. So a big issue for us is understanding when do we reach the limits where we are into super hot formations. This is something we have not been able to answer. We know it from past wells, but we want to be able to pick up that information while we're drilling. And so, but yeah, and what we decided to do is to have the casing down to 2,000 meters, possibly 2,100 meters, and then liner down to 2,500 meters. So the production stone is around 500 meters. Of course, there's uncertainty how deep we will get in the end, but this is at least the design criteria. The design parameters are for 450 degrees C, and somewhere probably, I would say, between 60 and 80 ppm of hydrogen chloride, and similar of silica in gaseous phase. So we estimate to get very similar fluids as from IDDP-1. And so this is the well design, except don't look at the material selection. We will be using nickel alloy for the liner, and then we will use mostly traditional steel for other casing. We will have a minor upgrade on the production casing by increasing chrome and molybdenum for increased corrosion resistance, and then we will use flexible couplings that are designed by Iceland Geosurvey, and we have tested in one of our previous projects. that allow the casings to adjust to the thermal stresses. And we will be used adjusted valves and wellhead for these conditions. This was one of the main issues from IDDP-1. The master valve got stuck, and so we put a lot of effort into working with companies on understanding and what solutions are needed, what type of materials and adjustments. And as I said, we will case off everything above the Superhot reservoir, and then a big factor as well is on the operational side. We have to make sure that the well is never operated below 80 to 100 bars, so we are not causing scaling inside the well. And we are also looking into methods to lower corrosion during warm-up of the well when you're transitioning from liquid phase to superheated phase, where you are mixing together superheated steam and water and condensing hydrogen chloride. That is the most vulnerable phase of the lifetime, I would say, of the well. Possibly it's more vulnerable when we have to rapidly cool it, but this is where most of the corrosion happens. So if we can limit the warm-up period time and also use some methods to adjust the pH downhole, this will help us a lot in protecting the well and allow for the flow testing without damaging to any of the equipment. So our planned date for drilling IDDP-3 is by the end of this year. We will start December probably, and all licenses have been acquired, and we are just in the phase of securing the equipment and finalizing all the research and design and other work. And then we are planning the second well in late 27, the injection well. Possibly it will be located as a potential pair with IDDP-3. This is something that we will be working on within the SHIFT project, trying to estimate if that is an option or not. And then we will carry out experiments on permeability and methods for that in 28. And this journey will end with a pilot power production in the last quarter of 28. Hopefully on the scale of few megawatts, possibly 3 to 7 megawatts, something like it. But our future vision is, with Icelandic geothermal systems, we can with time utilize this traditional kind of EGS ideology, but in higher temperatures. There will always be a challenge in basaltic formations with fluid loss but on the other hand, Icelandic water resources are probably one of the richest in the world. So water and access to water is much less of an issue for us. But this is something we will test in 28. We'll probably not go deep into it. And as I said earlier, it's more in the context of working on the boundaries, in the topmost section of the system, working on short production length. But as we go forward, we will definitely benefit from the general EGS development that's going on in the world, and hopefully this will be the future of how we can expand the production into more places through the plate boundaries, and Nesjavellir could harness geothermal from the source, from the roots of the system. But IDDP-1 or the other well we are planning now will not, of course, answer all this, but we will learn a lot from each pilot and then do more iterations as we go. But our hope is that we can at least start to scale up this technology in any form after this 3-year plan, so 2029 and forward. Thank you. And Alex, I guess it's over to you now for the questions. And maybe Alex, I just wanted to add that the IDDP project has always been very open. Everything or most things have been published of the work that has been done, and we operate this project that we are willing to potentially work with everyone that has technology, research methods, or things that could align with what we are doing, and I encourage you to be in touch or meet me at the WGC if you're there, if you wanna learn more or understand if there is a potential for cooperation. Okay, now over to you, Alex.
Thank you, Siggy. It was super interesting. I mean, of course, been personally following the project for, well, since the first project indeed, but to hear the structured approach of how this is now evolving is super exciting. And I think also in the international efforts on Superhot rock, definitely super interesting. And here, particularly also the openness of you to share those the data. They're now dribbling in quite a large number of questions, and they are in generally relatively technical. So I will just try to structure and group them in one form or another. But maybe starting first of all on the drilling. To drill to these depth levels, essentially, or to in this is you're using traditional geothermal drilling rigs and crews, or is there a specific aspect, kind of like for these projects that IDDP-1 and 2 kind of showed that kind of make drilling particular and needs to be looked at before you actually plan and start drilling?
No, I think this drilling job will be mostly business as usual. It's not exceptionally deep at all. This is just a traditional depth. This is, of course, the only thing we are doing different from traditionally done in Iceland is the casing depth. So going down with the production casing down to 2,000 meters. And also, I would say when we get into the Superhot formation, possibly we will be drilling with a total loss there. So, but this is something we are used to, but of course there is limitations in equipment and other to do some of the measurements and other that you want to do downhole, but since we drill with water in the deepest part, temperature is not an issue for the drilling equipment. So I would say this is mostly business as usual for drilling.
Okay, then I'm just kind of like trying to kind of get through this here, and I might not manage to group this as much as I kind of expected. On the cost estimates for these IDDP-3 phases, and looking at longer term, what, let's say, level cost of energy or unit cost do you expect to achieve in this context, or is this relatively open-ended for now?
I would say, the ETS part of our project is definitely the most uncertain, because there we are still in the phase of kind of understanding and developing what methods and we can use. But scaling up the shallow superhot geothermal wells, I would say that working with a theory of higher output than traditional wells, and that we are seeing energy prices that could come from this that are probably not very far from current prices. So that we get from just our traditional wells. We haven't had the final design of the wet scrubbing part, so we are still not. It's not transparent how much that adds to the cost. But I think with the cost addition that comes with the new equipment, the new solutions we're using, I think is reimbursed with the increased steam and higher enthalpy you get out of the well. So this might change when you start to go deeper, and this is something that will be part of the SHIFT project to better understand, to dive into to study the economy of this. But it's my hope that this will be within kind of generally Icelandic energy prices are very low. We are isolated energy system, and we cannot connect directly to other markets. So energy prices, long-term energy prices are low due to that, and but I still believe that this approach could work within the current prices.
Here, additional questions with regards to the temperature limit for the tools you use to measure the inclination and the bottom of the well. And is this available in real time? So here, I guess there is some technology development that particular targets, let's say, higher temperatures for measurements. But kind of what are the limits that you see for now on those technologies?
Well, I see mostly that there is not much available if you really wanna measure the bottom temperature. But most of the things we will try to do is during injection of water. So the well has been cooled when we do use some of the tools, but it looks like limited. We are limited to tools that can go up to 350. There are very few tools that can go above 400. There have been some reporting of tools, PT tools, and others that have managed to get closer to 500. But this is something we are mapping out at the moment, and having a dialogue with the tool producers, and to understand what we can use, what we can test. And this might even be a great venue for testing new technologies.
That puts us to a good question I wanted to say for the end, but essentially, I mean, this is like a test project like this is of course super interesting, not only for, let's say, for a national sector like Iceland, but also for international partners and companies. how do you engage with players that could become part of this and test equipment here in Iceland with the project? Is there something ongoing? I mean, you, of course, as part of the Shift project, you collaborate with organizations in Europe, but kind of what about technologies and companies trying to kind of get engaged?
Yeah, this has been through the IDDP project from the beginning. The you we have engaged with, you know, many different companies, even though they are not maybe part of the consortium or part of some you know, defined big research project. We have opened the doors to all sorts of researchers, to technology developers, and even companies that are working on their own technology and want to test it in this environment. And we always can, you know, see the benefits both ways. You know, if the technology is not to the market and someone want to test it with us, and then we get to understand as well, you know, the possibilities. So we are really structuring our approach to being able to drill these type of wells and build power plants from this type of technology. Our goal is not to compete on the technology side. So that's the reason for we're really happy to work with all sorts of technology companies.
Okay, there are definitely here way more questions than we're able to answer. Of course, I could kind of try to kind of get through this, but maybe I'll just take a few here, and maybe you try to kind of like answer them as quick as possible. So here, the first question: does the reservoir water flash over into steam in the wellbore or at surface?
In the reservoir, this is a dry steam. It's a
Okay.
low pressure, high temperatures.
Here the question is with regards to drilling near magma and the channel of innovation, but have you ever discussed COT as a supercritical fluid or other working fluids that could be injected?
Potentially in a closed system, but I would say that, you know, what type of any systems like that presumably have higher cost and requires, you know, more R&D. Our focus now is to kind of manage to get a flowing well, get the well integrity and the wellhead and everything working for a long time. Then kind of optimization of the power cycle and it comes later, I would say, for us. That's the reason for we are going to go for wet scrubbing. That's very simple, robust, but not the most efficient. But you know how to do it. And something like closed loop CO2 in Icelandic system it's just a way too big leap for the first step, I would say. But definitely interesting to learn more.
Here's the question, of course, other minerals. Is lithium an option here in Iceland?
Lithium is definitely not an option in this because, as I said earlier, there is only superheated steam. So
Okay.
what chemicals you have are the ones that go into the vapor phase when the water boils, not go into being salt. So lithium would stay in the salt that is left in the reservoir. But in general as well, lithium is not very high in Icelandic basement rock. But potentially some highly saline systems.
Okay, and then I'll just jump to two, let's say, combine two questions, and these will be the last ones. Cementing and casing. These are, of course, like really specific conditions. What's the pressure, the pressure, let's say, challenge here for these casings, and how do you do the cementing under these conditions?
Yeah, I would say the pressure is nothing that we haven't been dealing with before. We are using with available casing material that can withstand up to 200 bars or 250 bars, something like that. The cementing and the cementing method, that I would say is one of the biggest challenge. We saw this fail in both IDDP-1 and 2. I would say one is the material itself, the cement, that is not stable above 350, 400 degrees. The second is the placement of the cement and how we avoid the formation of water pockets, that if when the well heats up, the water pocket makes the casing collapse into the well. And this is something we're working heavily on at the moment. There are a few options that we are exploring, and so I don't know exactly now how we will do it. We are weighing our options and working with a few companies on different approaches.
Super interesting. And with that, I think our time is unfortunately done. Siggi, you will present at the World Geothermal Congress here together with other Icelandic colleagues. But I guess you're also looking very much to the exchange with other players in the Superhot arena, I assume.
Yes, absolutely. Yeah, I think that's a crucial part for us to because we are a very small ecosystem of experts here in Iceland, and we really, we need to work with a local community in the sector to get this off the ground.
Excellent. Well, then people will find you at around the Icelandic booth, of course, at the trade show, but also presenting, I guess. Siggi, thank you so much for taking the time, and it was great to having you. And we wish you, of course, all the best for the project and the different phases thereof. Thank you very much.